So two elimination possibilities, same electrophile. So the first question we ask ourselves, what kind of electrophile do we have? So this is secondary, this is secondary. So both of that is true for both of these. Then we look at the nature of the nucleophile, and we see that this one is reactive, this one's unreactive. So if it's reactive, that makes me think SN2 or E2, but I already told you it's elimination, so this one's going to be E2. And then this one will have to be E1. And how did I know that? Because, again, I said it's going to have to be eliminations. Now, the mechanisms are going to be a little different here, but the idea is the same. You're going to need to find beta hydrogens. Now, they're a little different with E1. The leaving group leaves first, and then you find beta hydrogens, or you think about rearrangements. So let's do the E2 one first and find the beta hydrogens. So I see at least two types of beta hydrogens for this one. So I'll label those. These are those hydrogens that are 2 sigma bonds away. So that means I'd have two different products. So if I labeled, we'll give them a label, HA versus HB, one's more likely than the other. So there's a couple things we think about for eliminations. We've thought about Zaitsev's rule, and that means more substituted. The alkene, right? So, right? That kind of thing. And then we also talked about conjugation / resonance. And that's actually more important. Right? More important. That you should have saw a couple times, quite a few times in your homework. Conjugation is more important than substitution. They're both important. So if I'm looking at this though, knowing these things, that conjugation here is more important. If I make a pi bond, I can make a pi bond here with HA, or I can make a pi bond here with HB. If I make a pi bond here, this new pi bond is next to this pi bond. That means it would be conjugated. And like I said, that's more important than Zaitsev's rule. Even though this might be more substituted, doesn't matter. We'll do the conjugated one. So that's the product we're going to make. Electrons go to the bond. There. There we go. That'd be one of the products. The conjugated version. E1 is going to be a little different, but let's see how we feel about E2 right now. So the other fun thing about this, remember we also have, this way it gets complicated, E and Z to worry about, where E is more stable, right? E. So here technically there's an H here. This would have this has higher priority, and this one has higher priority. So right now it's in the E form. So this would be the most stable version. You could draw it as the Z, because I don't have any wedges and dashes. You're not worrying about anti-periplanar stuff. So you could draw it like this, but this would be the Z product and not as likely. So Z, but I would say probably not. And then this would be the better product. You can see how these things can get pretty complicated pretty fast. So for the E1 now, this one, the first step is actually going to be the leaving group leaves. All right, so that's going to be our slow step, makes the carbocation. So this is a secondary carbocation. So we're worried about rearrangements here. So we're looking for things single bonds, 2 bonds away. And there is an H here. And there's an H here. It's like the same as those beta hydrogens. But we're actually going to rearrange. So this H is going to rearrange the electrons there. And it does that because now you've created a tertiary allylic carbocation, which is more stable. So again, you're looking for beta hydrogens. Now that you're done rearranging, I think you're done. Can't get it better than that. Looking for beta hydrogens. So the one you just left, and then there's these ones. And what's going to probably be, right, they both, if I made a pi bond here or made a pi bond here, they both have resonance. So if that's true, then I want the more substituted one. This would give me the more substituted one. So what's going to happen, that's going to fall off. And you're actually going to get to the same exact product, but from a different mechanism, and then plus H plus. So it's kind of a different way, different mechanism, but you get to the same product.